Thank you, Dr. Monet. I'd like to now introduce Dr. Randall Lee, T. Randall Lee, who earned his PhD from Harvard University and had an NIH postdoctoral fellowship to continue his studies at Caltech. He was awarded the Camille and Henry Dreyfus New Faculty Award, the National Science Foundation Career Award, and was the first winner of the University of Houston Undergraduate Research Mentoring Award. He's authored over 150 journal articles, book chapters, and patents, and is now the Cullen Distinguished Professor of Chemistry at the University of Houston. Please welcome Dr. Randall Lee. Try to keep you to talk for 20 minutes.
I'll do my best. Thank you. Thank you for the kind introduction, and I'd like to thank the organizers for the opportunity to come here and tell you about some of the work that we've been doing in my group at the University of Houston. Of course, I had a little difficulty getting here. I encountered the Newark problem with transport as well and was delayed there, and was also the fortunate recipient of food poisoning while I was in the Newark airport. So hopefully you will bear with me through the presentation, and if you see me darting out, it has nothing to do with you, I assure you. Anyway, what I'd like to talk about today is some work that my group has been doing in shell core nanoparticles. Actually, we work in two areas in this realm. We do optical nanoparticles and magnetic nanoparticles. And so today what I'd like to focus on is some optical nanoparticles, the work that we've been doing in that particular area. Now, I'm sure all of you are familiar with semiconductor nanoparticles. We've actually had some mention of them in the talk so far. And these are really, really interesting materials where one takes a nanoparticle and you can shine light on these nanoparticles. They absorb light and then they re-emit light, okay? And so what's really cool about them is that the wavelength of emission depends on the particle size. So if you're good at doing synthesis, you can manufacture a series of nanoparticles and you can have them emit frequencies, whatever you like, just depending on the particle size. So they're very, very useful and used in a wide range of applications. My group, on the other hand, is interested in something that is arguably much more boring from the optical point of view. And these are just simple metal nanoparticles. Many of you might be aware of gold nanoparticles, for example, that have been used for centuries in stained glass. So the beautiful reds that you see in stained glass has come from the optical absorption, the plasmon resonance of gold nanoparticles. So what happens with metal nanoparticles, like gold, silver, palladium, and copper, is that the light is absorbed and converted to heat. So unlike semiconductor nanoparticles, these nanoparticles will absorb light and get hot, okay? So that's very useful. Unfortunately, the absorption wavelengths, however, are quite limited in what nanoparticles can encompass. For example, here is an absorption or an extinction spectrum of some metal nanoparticles. Palladium's plasmon resonance occurs just above 200 nanometers, silver occurs at about 400, and gold just about 500 nanometers. If you make an alloy out of gold and silver, then that plasmon resonance falls just in between that of gold and silver. So really, your absorption wavelengths with simple metal nanoparticles are limited to from about 200 nanometers to about, let's say 550 nanometers. Now, about 10 years ago, in collaboration with my colleagues at Rice University, we developed a nanoparticle architecture which we call a nanoshell. And if you take a silica core, a non-conducting core, and then you coat it with a metal, this gives some tunability to the plasmon resonance. So for example, if you have a 100 nanometer silica core and you coat it with a thin gold shell, where the gold shell is about 20 nanometers thick, the plasmon resonance will appear at just above 700 nanometers. And as you make the shell thinner and thinner and thinner, the plasmon resonance shifts further all the way into the near infrared. So now we can take simple metal nanoparticles, and if we put them in this architecture, we can have tunability that allows us access to the near infrared. So here is a slide showing you these particles. Here are some nanoshells with a thick shell, and as we make the shell thinner and thinner and thinner, you can see the color changing, and then when we're absorbing in the near infrared, it appears clear, okay? Now, why is the near infrared interesting? Of course, most of you, I'm sure all of you are aware, that in the region from about 750 nanometers to about 1200 nanometers, there are no chromophores in the human body, in the tissue or blood, that absorb at those wavelengths. And so we can make nanoshells that absorb at these wavelengths, which means that we have a way to optically deliver heat to the body through a nanoparticle system using metal nanoshells. So some work that's already been done, my colleague Jennifer West at Rice University has demonstrated the technique of laser tissue welding. And so what you do here is just take a piece of tissue and slap on the surface of it some nanoparticles, and then you shine an infrared light, and the nanoparticles get hot and fuses the tissue together right at the point where you put your nanoshells. Okay, and so the only part that gets hot are the nanoshells themselves, so you can really localize the heating. So this process has advantages over trying to do laser tissue welding with, for example, ultraviolet wavelengths, because those wavelengths will cause extensive damage to the tissue. If you do the nanoshells, you can take two pieces of tissue and layer your nanoparticles in there in a very localized area, and then when you shine your laser light, you can get efficient welding without too much damage. And so some of the sorts of applications that people are thinking about using this, of course, plastic surgery. In particular, nanoshells can offer reduced scarring in such an application. But perhaps the most important one is in the treatment of wet macular degeneration. And in that case, this is a problem that many elderly people suffer from when they lose their eyesight. And there are leaky capillaries in the eye, and of course, one can use nanoshells to close off those leaky capillaries through this concept of laser tissue welding. So you can imagine targeting the leaky capillaries in the eye and then doing the laser tissue welding, where you will have a highly localized heating process. And then what can ultimately happen, of course, is photocoagulation of the capillaries through this laser tissue welding. And so there are some interests along those lines. Perhaps the application in which these nanoshells have received the most publicity is in cancer therapy. And so, for example, since nanoshells absorb in the near infrared and they have a gold surface, it's quite easy to conjugate an antibody or a targeting agent to the surface of the nanoshells, and then add the nanoshells to a target and either allow them through the targeting agent or through the increased vascularization near the tumor to build up in higher concentration than in normal cells. Then apply your external laser and then kill the tissue through optical heating. Okay, so here is an example of some tumor ablation studies done where a near IR laser was used to blast a set of tumor cells with no nanoshells present. And then here is the same experiment done where we've treated the nanoshells that have been conjugated with an antibody targeting agent. In another experiment demonstrating the ability to deliver heat using nanoshells, and this is a very complicated and expensive experiment using magnetic resonance imaging. If you take a piece of tissue and you blast it with a near-infrared laser, basically nothing happens. The tissue doesn't change temperature, nothing goes on. But if you inject nanoshells just under the surface layer and then blast with a near-infrared laser, you can, using magnetic resonance imaging, monitor the heating of the tissue directly. And so that's a real fancy way of demonstrating it. There's a much simpler way of demonstrating the same concept. Here's a chicken leg. Take a chicken leg, blast it with a near-infrared laser, nothing happens. Okay, but if you inject nanoshells under the layer, you see you can burn a hole in the chicken leg using the laser. So I think this is a cheaper but perhaps more straightforward demonstration of that effect. Now, of course, if you're thinking about cancer therapy, there is always the question of, did you kill everything? Did you get everything that you were trying to get rid of in the therapy? And so along these lines, we are also developing hydrogel-coated nanoshell particles for drug delivery applications. So in this case, what we do is we take a metal nanoparticle and coat it with a thermally sensitive hydrogel polymer in which we can incorporate a drug molecule. So these little black dots are supposed to be the drug molecule. And if we apply our near-infrared laser, of course, the nanoshell particle will get hot, causing the hydrogel to collapse and release the drug. So in this case, we can imagine a dual therapy where we're doing drug release and heating at the same time. Or if you just want to do simple drug release, you can, it depends on how much light you want to, how much light input you have, exactly what therapy you're going to do. So a possible benefit of this approach is that you can do drug release and thermal ablation at the same time. So here's an example of a hydrogel polymer, a polynipam polymer in its swollen state and collapsed state that shows you the sort of dynamics that are involved in this sort of process. And in our research, what we're doing is we're taking the metal nanoparticle and we're treating it with a polymer initiator we put on the surface, and then we add our monomers. Usually, most of the work that we've done so far is using polynipam or a copolymer of polynipam and acrylic acid, which allows us to have a hydrogel that collapses just above physiologic temperature. And so we then do this polymerization and form our hydrogel-coated nanoparticles. And so here are some SEM images of some of the particles that we made. It's not real clear here, but these are just simple gold nanoparticles with no coating. And here are some of the hydrogel-coated gold nanoparticles. You can see they have this little outer coating on the outside. That's the hydrogel coating on the nanoshells. Some TEM images of them. Again, here is the gold particle, and you can see just on the edge, you can see this hydrogel coating, and here's a magnification. You can see the hydrogel around here. And of course, it looks very thin in these images because the technique that we're using is TEM, and in the process, we didn't take any precautions to exclude the evaporation of water when we put these things under ultra-high vacuum. So the thicknesses are less than what we measure with dynamic light scattering. We can do EDX analysis that proves that we have gold there that's in the center. Of course, these initial studies that we did were not with nanoshell particles themselves. This is just simple gold nanoparticles to try to work out the technology. So here we have an example of the UV spectrum. This is just a bare gold nanoparticle. This is a hydrogel-coated nanoparticle, and as we build up the thickness of the hydrogel nanoparticle, you can see that the plasmon resonance starts getting buried. Now that can be quite important if we're trying to modulate in the visible region because scattering is getting to be competitive with absorption. However, for the nanoshell applications, we're going to be targeting in the near infrared, and so scattering effects probably will not be such a concern for us there. Here are some hydrodynamic dynamic light scattering measurements of the diameter of our hydrogel particles compared to just bare gold nanoparticles as a function of pH. And so what you find is that at high pH, the nanoparticles are in their expanded state, the hydrogel is swollen. And then as you lower the pH, there is a point at which the diameter drops precipitously and collapses, giving your lower diameter here. In comparison, the bare gold nanoparticles show no variance with pH in terms of their diameter. This property is reversible for the hydrogel-coated nanoparticles. More importantly, the thermal collapse and reconstitution profiles illustrate similar behavior. Bare gold nanoparticles are essentially insensitive to changes in temperature. The hydrogel-coated particles, as we heat them up, the volume collapses, and as we cool them back down, they grow again. And importantly, if we use an infrared laser tuned to about 530 nanometers, since these are just simple gold nanoparticle cores, the bare gold nanoparticles show no variation with laser on and laser off. But if we take the particles, measure the diameter, blast it with the laser, you see the diameter drops precipitously, allow it to cool, measure the diameter again, blast it, and so forth. And we can do this regular repeat and reconstitute behavior of these nanoparticles. Now, of course, the question remains, do nanoshells behave like regular gold nanoparticles? And in our experiences with nanoparticles in general, that's not an obvious question that they would. So we then turned our attention to some nanoshell particles. And first I'd like to mention how these things are made. Okay, to make a gold nanoshell, we typically start with a silica nanoparticle core, and we treat it with a silane agent to leave amino groups at the surface of the silica nanoparticle core. These amino groups are attractive towards small gold particles, gold colloid particles, about 2 nanometers in diameter. And so then we have these silica core particles with these little tiny gold particles decorated on the outside, and we add a reducing agent in the presence of gold salt to then grow the gold shell. The gold seeds act as nucleation sites, and you get a complete shell. Here is this process demonstrated schematically. Here are the seeds on the particle. We start the reduction process, the shell grows, and then finally we have a complete shell. Now, as shown here, it looks quite simple. It's an involved process. It turns out that even my best students with considerable experience in making these shells can reproducibly make these particles about 1 out of 3 times. Okay, and it's a very complicated process. It's not easy to do. And we have a lot of people out in the scientific community who write to us and say, you know, we tried to make your particles and you know, we're not having success. And, you know, we understand it's not easy to do. But there are all sorts of things about, for example, the reducing solution that you use to prepare to grow the gold shell. You've got to age it a certain number of days at a certain temperature. You know, you absolutely have to do it that way or it doesn't work. There are a lot of little tricks in there. And so it's a quite complicated process. So, but of course it does work. I mean, we do have evidence that it works. Here are, for example, silica core particles that are 300 nanometers in diameter that have gold seeds attached to them. Here are shells grown on these same particles, and you can see the shells in some cases look pretty smooth, sometimes quite rough. We can make shells where the thickness varies from, say, 10 nanometers all the way up to about 25 nanometers. And here are our spectra, extinction spectra, that illustrate the optical properties that we could have predicted theoretically for these type of particles. For example, if you have a 25 nanometer shell particle, the absorption here is about, say, 750 nanometers. If you make it thinner to 17, the absorption maximum moves out to around 800, and if you make it 10 nanometers, it moves out to about 900. Okay? We can make them smaller than 300 nanometers. Here are some 90 nanometer silica core particles, okay, nanoshell particles, where we've grown the nanoshells on 90 nanometer silica cores. These particles have shells that are about 7 nanometers thick. These are about 13. And again, a simple gold nanoparticle would absorb at about 530 nanometers, but our particles are absorbing at, for the 13 nanometer shell, at about 750 and around 800 for the 7 nanometer shell. Can we grow polymers on the outside of these nanoshell particles? We use the same process that we were doing with the simple gold nanoparticles. Take them, treat them with oleic acid and our monomers, and grow the shell. Here are some SEM images of the bare gold particles, and these are the hydrogel-coated particles, which again suggests that the process is working for the nanoshells. Here are TEM images, bare and then hydrogel-coated, that confirm further that we're able to do this sort of process. And here are, unfortunately, we weren't able to get a laser of the right wavelength to do the optical modulation experiment, but we can simply heat the sample chamber up and measure the diameter directly. So for nanoshells themselves have a constant diameter as a function of temperature, 2540, 2540. We're just alternating the temperature of the chamber. But our hydrogel-coated particles, you can see that as we heat them up, the volume drops, and then cool it back down, it reconstitutes. And so we anticipate that they have the same behavior as the other ones, so that's quite good. Now that brings us back to this synthesis problem, okay? And we've been working, my group is a synthesis group, and so I don't have much further to go. And so to address the synthesis problem, we have developed a new type of nanoparticle that it turns out to be much easier to make, but has a lot of the same properties. And so, for example, these, we call them metal-metal nanoshells. We can take a silver core particle and just pour it into a specific gold solution, and the gold shell will immediately grow around the silver nanoparticle core. So it's really a two-step process. You make the silver core and treat it with the gold solution, and you've got your nanoshell. So here are some of these, TEM images of just the core particles, and then ones that have the gold coating on them. Here are an example of these particles in solution, the silver core particle, and as we grow the gold shell, we're moving toward the near infrared. Here are the UV spectra that illustrate this. A silver core particle is just above 400 nanometers, and we can vary the absorption wavelength all the way out to about 950 nanometers with this very simple and easily reproducible process. So an important thing to note is that for the older technology nanoshells, it's hard to get below 100 nanometers in overall dimensions. These particles we can make down to about 40 so far. So we can get to much smaller dimensions and more access to different biological systems. We've also made some particles that we call nanodonuts. And you can see here's the nanoparticle with the hole in the middle. These nanodonuts also have an absorption in the near infrared, and we're exploring them for use in various applications. So one can imagine using nanoshells in a lot of different biological systems, in vivo, ex vivo, a lot of sensing applications, optical shielding, even solar energy conversion, because you can design these particles to absorb light over such a wide range of wavelengths. All right, I'd like to thank my colleagues, of course, at Rice University, who I've been working with for around 10 years now. A lot of the work that you saw today was done by some of the co-workers at the MD Anderson Cancer Center. There's a company now that makes and sells nanoshells, nanospectra. And I'd also like to thank these groups for their funding. Of course, my group has been so much fun over the years, and of course, none of this would be possible without them. I guess we have about 30 people overall now. Our group is, I've talked about one aspect, our metal nanoshell project, but we're actually a big group, and we do synthesis. We make things to try to solve problems. But we don't only work. Here's a recent picture of the group at an outing at a ranch that one of my students has. His family owns a ranch out near San Antonio, and a trip to the beach. A lot of the work that you saw here was done by Dr. Jun-Hyun Kim. He was actually a graduate student with me. He's now doing a postdoc at Northwestern. He did the bulk of the hydrogel-coated work that you just saw. Yu Lim is working in the magnetic nanoparticle area, and he and some other students, of course, are creating trouble with the drinks here. And as I said, it's not only work in the Lee group. Students tend to have a lot of fun themselves and get silly times singing in public and all sorts of things like that. So thank you for your attention.